Once again, we're going to be trying to optimize a value. This time we are looking for the dimensions of a box with a volume of 1,000 cubic centimeters and a minimum possible surface area. So in this case, once again, we'll be talking about a rectangular box, something similar to what you see right here. Bring in parallels to all of those sides. Now for this one, we are going to be looking for the minimum possible surface area. So let's go ahead and define three dimensions for this. We'll use x, y, and z to represent the length, the width, and the height. The quantity that we are attempting to minimize is the surface area. The surface area for a rectangular box. The box is comprised of a total of 6 rectangles. The base and the top of the box would both have dimensions of x by y. So xy for the area of the bottom, xy for the area of the top. There is a front side and a back side to the box that are both rectangles that are x by z in their lengths. And then we have the two lateral sides that are rectangles with dimensions of y by z. So there are 2 of them, so we'll include a coefficient of 2. Additionally, we know that the volume of the box is supposed to be equal to 1,000 centimeters. And for these dimensions, that volume would be x times y times z. Now with that in mind, that is why we're going to be performing a substitution on this. The substitution on this, we're allowed to substitute any of the variables into our given surface area. What I'm going to recommend is that you stick with z on this one so that we can set up a function of x and y. So z is equal to 1,000 divided by xy. We're going to substitute that into the function that we have here. That way, s of xy is going to be equal to 2xy plus 2x times our substituted variable plus 2y times our substituted variable. And that substitution is going to be 1,000 divided by xy. Now if we perform some algebraic manipulations to these fractions that we've just created, and in anticipation of the derivatives that we're about to take, for this we can cancel out the x's, multiply the 2 times 1,000 to get 2,000, and refer to this as y to the negative 1 power. We can do similar algebra to the third term here and call that 2,000 times x to the negative 1 power. Now please do note that as we're going through here, it is impossible for x and y to be equal to 0. X cannot be 0 and y cannot be 0. This is due to the fact that that would contradict the volume being equal to what it's equal to. So with that in mind, let's go ahead and take a couple of partial derivatives and solve this using the method of critical points. So with that in mind, partial derivative with respect to x is going to give us 2xy will become 2y. 2,000y to the negative 1, this would be treated as a constant term with respect to x. And then over here, applying the power rule, this would be negative 2,000 times x to the negative 2 power. We'll be setting this equal to 0. For the partial derivative with respect to y, we will see some very similar derivatives here. However, this time we'll be treating x as though it is our constant and y as our variable. So the first term will become 2x. The middle term, applying the power rule, will be negative 2,000 y to the negative 2 power, and the third term will vanish as it is equal to a constant. Next up, let's go ahead and solve this using a substitution. I would recommend either solving the first equation for y or the second equation for x. Now if we solve that first equation for y, we can do so by adding 2,000 x to the negative 2 to both sides. We'll call this y is equal to, and then dividing by 2. So 1,000 x to the negative 2 power. Or more succinctly, this is 1,000 over x squared. We're going to perform this substitution into this equation. This will give us 2x minus 2,000 times 1,000 over x squared raised to the negative 2 power is equal to 0. Simplifying this will be 2x minus, so the negative 2 power means flip top and bottom and square the result. So this will be x squared over 1,000 squared is equal to 0. Continuing to simplify this will become 2x minus, let's see, that would be 2,000 x to the 4th power divided by 1,000,000. And simplifying this fraction will be 2x minus, we'll call this x to the 4th power divided by, take 2,000 divided by 1,000,000, that reduces down to 1/500th. That'll be equal to 0. Let's go ahead and clear out the fractions by multiplying both sides by 500. We'll get 1,000x minus x to the 4th is equal to 0. It should be pointed out, though, we already know that x cannot be equal to 0, so we could divide both sides by x as well. So 1,000 minus x cubed is equal to 0. This simplifies to x cubed is equal to 1,000, and therefore taking a cube root of both sides lets us know that x is going to be equal to 10. Now that's the numerical value for the units. We head back up top and see that we were dealing with centimeters. So x would be equal to 10 centimeters. Then we can head back to the substitution that we used for y and plug in x equals 10. So y would be equal to 1,000 divided by 10 squared. That'll reduce down to 10 centimeters as well. And then finally, if we plug x and y are both equal to 10 into this substitution, we will get the same thing for z. So z is equal to 1,000 divided by 10 times 10, which will simplify to 10 centimeters as well. So as it turns out, when you want a rectangular box of minimal surface area, you are going to be dealing with a cube. All three sides are the same length.